A couple of things. Welcome back from spring break and all, but the fact of the matter is you officially were supposed to have something due on, Saturday or whatever, Sunday, on a quiz and stuff like that, but I pushed it back. So I'll let you guys know, in case you're not keeping up, due within a week here, you've got quiz number 6. If I click on quiz number 6, I want to let you guys know that I gave you 3 attempts on this because it was spring break, but it is due March the 12th. So if you haven't done it yet, get on it. Don't wait till the last minute and stuff like that. So let you guys know. But it's on just section 3.4a. So it was still on that last part about taking derivatives and max minning and stuff like that. It was supposed to review, but there's one little section we didn't have on the quizzes that actually was due during spring break, but I actually pushed it back a little bit just to make you guys feel better about yourselves and stuff. So it is due actually, now it is due on, was that Tuesday or something like that? So there you go. All right. And like I said, your test, I'll be passing back at the end of class. I've put them under your grades. If you put grades, that's easy access for me, so you can actually go see it under grades on the Canvas system. I have not imported it into the Hawks gradebook system yet, which will obviously, with all that other stuff, it shows you what your grade is and stuff like that. But be careful on the Hawks gradebook. One other little problem that I've discovered is every time I have a homework set due and I put a date on it, when I don't import those grades immediately, it puts zeros in for you guys. You don't have a 0. I just haven't actually put the grades in yet, but when it doesn't receive a grade, it just automatically throws a 0 in there. So your grades look lower than they truly are. I'll go back and fix that. I'll make sure they're blank until I actually put the grades in. But I just discovered this like over spring break, so don't panic and stuff. All right, so we're working on today, chapter 4, starting out with section 4.1a, higher order derivatives. And I talked a little bit about this last time, but the idea of higher order derivatives, and it's the derivatives of derivatives, basically. And so you can have yourself a function, f of x is equal to 3x squared plus 6x to the negative 2 plus 5x minus 1 plus 4 square root of x. There you go. Give you a function. Higher order derivatives. So, first thing you want to do is clean it up, of course. So f of x, cleaning this thing up, this is 3x squared plus, this could have been written 6 over x squared, same thing as 6x to the negative 2, plus 5x plus minus 1, plus 4, I don't do square roots, that'll be x to the 1/2 power. So we all know how to take the first derivative. First derivative is going to be, derivative of 3x squared is 6x, derivative of 6x to the negative 2 is going to be minus 12x subtract 1, negative 3. Derivative of 5x is 5. Derivative of minus 1 is 0. The derivative of 4x to the 1/2, on 1/2 of 4 is 2x to subtract 1, negative 1/2. There's my first derivative. This idea of higher order derivatives are the derivatives of derivatives. So we're talking about the second derivative. So this would be f double prime of x. If I use the Leibniz notation on this, this would be d squared y over dx squared. The little 2's up there mean it's the second derivative. So what's the derivative of 6x? It's the derivative of the derivative. Derivative of 6x would be 6. Derivative of minus 12x to the negative 3. Negative 3 times 12 is what? Plus 36x to the subtract 1, negative 4. Derivative of 5 is 0. Derivative of 2x to the negative 1/2 would be negative. 2 times the negative half is negative 1. X subtract 1, negative 3/2. There's my second derivative. The third derivative would be d cubed y over dx cubed. That little 3 meaning the third derivative of your function here would be equal to derivative of 6 is 0. Derivative of 36x to the negative 4. Well, bring down your negative 4, so 36 times negative 4 is negative 144x, subtract 1, the negative 5, and then bring down your power for the derivative of minus x to the negative 3/2. bringing out the negative 3 halves with that negative makes it plus 3 halves x subtract 1, negative 5 halves. And you can go on forever. After a while, with these the classic Newtonian notation, after about the third or maybe the fourth derivative, you can throw 4 hash marks if you want to. Eventually, we actually start using Roman numerals. So the fourth derivative, the IV, in terms of x there, would be the d4y over dx4. That's your Leibniz notation. Would be equal to derivative of negative 144x to the negative 5. Negative 144 times negative 5 is 720x subtract 1, negative 6, plus the derivative of 3 halves x to the negative 5 halves. So negative 5 halves times negative 3 halves would be a minus 15 fourths x to the negative subtract 1, negative 7 halves. And you can literally go on forever on these higher orders. In chapter 4, explicitly, we're going to be focusing now on the second derivative guy. The derivative of the derivative, that quote-unquote rate of change of the rate of change. Okay? Rate of change means derivative, so the rate of change of the rate of change would be the second derivative. Okay? So, what the second derivative measures? Well, let's analyze. The first derivative measures what? When we looked at the first derivative, we measured intervals of increase and decrease. That's really what we're focusing on. When the first derivative was greater than 0, it was increasing. When the first derivative was less than 0, it was decreasing. So we were either going up or going down, because this derivative does represent this quote-unquote slope of the tangent line. Okay? So when we were doing these number lines and stuff, we were trying to figure out what was increasing, where it was decreasing. And when we took the first derivative and set it equal to 0, and where the first derivative did not exist at, we call that a critical value. You remember, this is your max-min points. How to maximize or minimize anything, you take derivative, you set it equal to 0 and solve it, and give you the x-coordinate. Okay, and then from that, we either threw it on a number line and figure out intervals of increase and decrease. And we analyze this stuff. You go up, go back down, made it a maximum. You go down and go back up again, you made it a minimum. Does that make sense? Now, this is what we're focusing on in chapter 4. We're going to be focusing on the second derivative. When you take the second derivative and set it equals 0, and possibly where the second derivative does not exist at, these are going to be called inflection values. And when you get a wide coordinate, it'll be called an inflection point. Like these were called critical points, these would be inflection points. Now an inflection point is where you change quote-unquote concavity. So what the second derivative measures is something called concavity. Something called concave up. That's where the second derivative is greater than 0. And you have something called concave down. That's where the second derivative is less than 0. Concave up means it's going to be U-shaped up. Concave down is going to be U-shaped down. So, what exactly is going on here is this inflection point is where you literally change concavity. This is where the second derivative is equal to 0. I'm going from being concave up to being concave down. That's what you're looking for. Or it could be the other way around, concave down to concave up. These guys are your quote-unquote inflection points. Okay? But the key word here is we're going to be looking for the word intervals of increase and decrease and intervals of concavity. And when you hear the word intervals, what were you supposed to do? Draw a number line. When I asked for intervals of increase and decrease, you drew a number line. When I asked for intervals of concavity, you are going to draw a number line. increase and decrease was a number line for the first derivative. Intervals of concavity is going to be a number line for the second derivative, and you put your inflection values on the particular number line like you put the critical values on the number line for the intervals of increase and decrease. You're going to be doing the exact same thing with their next derivative up, the second derivative, okay? And then later on, in this particular chapter, we're going to start blending this stuff together. Where we're comparing increasing to concave up and kind of blending that and look at what the general shape of the graphs are going to look like. So, in terms of your notes, in terms of the application of the derivative, this higher order derivative, we're going to be looking at, most important, the second derivative of this stuff. I mean, you can go on and do third and fourth and so forth derivatives, and we're going to be determining concavity. And there's two types of concavity. Concave up, U-shaped up, concave down, U-shaped down. All right. So, the blank blank second derivative, f double prime, if it exists, its derivative is the derivative of the first derivative. Well, in English, this is the second derivative. The second derivative, f double prime, also known as d squared y over dx squared to get that Leibniz notation, or f double prime of x. This is your second derivative, okay?
Any particular reason why you're putting the second power in different locations on the Linux? No.
Yeah. It's German. Leibniz was German. So they're very, how do I put this politely? Anal retentive in terms of their mathematics. All right. What exactly is the derivative? Now, we all know this. I'll explain why the notation is what it is. This is a good question. You understand that d over dx means take derivative, right? This means d over dx, take derivative of what follows. Now, what is the second derivative? The second derivative is the derivative of the first derivative. What's the notation for the first derivative? So this stands for take derivative of the first derivative. The first derivative is this dy over dx, that classic Leibniz notation, delta y over delta x. We turned it into dy over dx. Now look at it. This means take the derivative with respect to x of the derivative, dy over dx. Now Leibniz, put it together. Do you see there? I got two d's but one y. So that's d squared y, so we put the square there, over, what's on the bottom? dx with the dx. What's that? That is dx squared. That's German, how they came up with the notation. So they put the 2 here, and they put the other 2 in the denominator over here, and yes, they are in different locations. And it's the Leibniz notation applies in 2 different regions. But that's the reason why it does. It is what it is. Okay? Number 2, a curve that is concave up lies blank. The lines tangent to the curve. Okay? And that's concave upward lies, and the key word here is above the lines tangent to the curve. Now this is, they're trying to get you this idea of what exactly does this concave upward mean. Concave upward means it's basically U-shaped up. And if it's U-shaped up, the slopes of the tangent line rates are actually going upward. The rates of the rates are positive. They lie above and the tangent lines are that first derivative. Okay? And of course, a curve that is concave downward lies below the lines tangent to the curve. Okay? And continuing on with that, it's not that important in terms of this. What I really want you guys to know is general shape. Concave upward means it's going to be U-shaped up. Now, I mean, as you relate it to the derivative slope of the tangent lines, you're right, the concave upward does lie above the tangent lines to the curve, and concave downward is going to be U-shaped down. That's going to be lying below the tangent lines to the curve. But suppose that f is differentiable on an interval between a and b. If f prime is increasing on a, b, then the graph of f is concave upward on the interval between A and B. All right. Now we're going to start playing games with English. Hang with me here. When you hear the words increase and decrease, what does that mean? How do you calculate increase and decrease? You take derivative, and where the derivative is positive, you increase, and where the derivative is negative, you decrease in terms of the original function. But we're not talking about f. We're talking about f prime. When f prime is increasing, increase means take derivative and make it positive, right? So you're taking the derivative of the derivative. So it's when the second derivative is greater than 0. But they're trying to get you to look at it as it's the derivative of the derivative is greater than 0. This is what it means to be concave upward. And similarly, if f prime is decreasing, the rate of change of the derivative is decreasing. That's your second derivative, is decreasing on the interval between A and B of the graph of f is, this is going to be concave downward. This would be where your second derivative is less than 0. And this idea of f prime decreasing. Decreasing means you took derivative of f prime. That's that f prime is being less than 0. That is what we're talking about in terms of concave down. Okay? So, in terms of this, suppose that f is a function and f prime both exist on an interval a and b. If f double prime blank for all x in a, b, and f prime is blank and f is concave upward. Well, to be concave upward, what's the big deal? This is what we're trying to get you to go. Concave upward means my second derivative is greater than 0. Concave upward, the second derivative is greater than 0, which means that the first derivative is increasing. The derivative of the derivative. This is the second derivative. So we're talking about the first derivative, so the derivative of that would have to be increasing. The derivative of the derivative is increasing. That means the second derivative is going to be greater than 0. And similarly, for f double prime to be blank for all x in the interval of ab, then f prime is blank if f is concave downward on the interval between a and b. To be concave downward, the second derivative is going to be less than 0, and which means the f prime is going to be decreasing and f is going to be concave downward. The derivative of the derivative. So they're trying to understand the relationship between the first and second derivative. The second derivative is the derivative of the first derivative. So instead of looking at the original function, you look at the first derivative, and then you decide where the first derivative is increasing. That'll be concave upward. And where the first derivative is decreasing, that'll be concave downward. So they're trying to put the two concepts together. The derivative of the derivative is going to be positive. That would be concave upward. Or the derivative of the derivative is going to be negative. The first derivative is decreasing. That'll be concave downward. If the graph of a continuous function has a tangent line at a point, possibly a vertical line, and the graph changes concavity at a point, then the point is called what? Well, we're talking about changes concavity. We talked about that just a few minutes ago. To change concavity, that'll be going from concave up to concave down, or it's going to be going from concave down to concave up. What do we call that particular point? That's called a point of inflection. An inflection point. There you go. A point of inflection. It's where you change concavity at. And officially, it's where the second derivative is equal to 0 at. Okay? Now here's a classic term for that. Those values x equals c in the domain where the second derivative at c is equal to 0 or the second derivative does not exist are called the blank blank of x. And I will rarely ever call it this thing, but they're called the hypercritical values. The hypercritical values are basically where the second derivative is equal to 0 at. I just call them the inflection numbers, okay? But hypercritical if you want to go that route with these guys. Again, being technical on your terminology here. Suppose that f is a continuous function. To determine points of inflection, so here's your steps. If I want to find the points of inflection, what's the first thing I got to do? Inflection points deal with the which derivative? So the first thing you got to do is you got to find the second derivative. Take derivative of the derivative. Then to find these inflection points, you need to find the hypercritical values. What does that mean? I'm going to find the values where x equals c, where f double prime of c equals 0, or f double prime of c is undefined, does not exist. I want to take the second derivative, set equals 0, and solve. Call them hypercritical values. It's the inflection numbers, okay? So if you think about this, and this is the most important part, how did I do when I did the first derivative stuff and I looked for max mins? I had a function. I took the first derivative. First thing I did was I set equals 0 and solve, and I got my critical number. The next thing I did was I threw them on a number line, right? The next thing I did was I did test values into the first derivative around those number lines to see when they're positive and when they're negative. And then I figured out increasing, intervals of increasing, intervals of decreasing. Now, what I'm doing is with the second derivative. First thing I got to do is find my inflection numbers, my hypercritical values. I'm going to take the second derivative, set it equals 0, and solve. And where it doesn't exist, I'd always look at that. The next thing I'm going to do is I'm going to draw a number line. I'm going to put these hypercritical values, my inflection numbers, on my number line. And then what I'm going to do is I'm going to do test values around it. I'm going to do test values in the second derivative. And when the second derivative is positive, it's going to be concave up. When the second derivative is negative, it's going to be concave down. It's the same procedure on a different derivative. That's the concept. That's the most important thing I can tell you right now about this stuff. Using the hypercritical values as endpoints of the interval, determine the intervals where f double prime of x is greater than 0, f is concave upward, and f double prime of x is going to be less than 0, f is concave downward. It's that number line and doing test values on that thing. I'm doing the same thing what we did in chapter 3, except with the second derivative. Okay? And quote, points of inflection occur at those hypercritical values where f changes concavity. And this is why they actually use the word hypercritical instead of my inflection numbers, because to officially have an inflection point, you have to change concavity. So I got to look at my second derivative number line, and I got to go from positive to negative, or I got to go from negative to positive. If I got one of those interesting number lines where I go positive, hit a point, and get more positive, it's not officially going to be an inflection point. It's just where you just stop changing concavity for a second, but you keep going in a positive direction. You literally got to go from negative to positive or positive to negative. Okay? Yeah. Well, number one, if you are using your phone during class, number one, that's illegal. You get actually dismissed from the room for that. You got to pay attention full up here. The other issue I have about your test, since you brought it up, is this. It's interesting that I had such a wide range of grades on my test. The average was pretty good on the test, but I had a bunch of folks who just completely bombed the multiple choice or completely bombed the free response. They would do well on one, but not well on the other. Now that means you guys have to have a technique of trying to figure out your careless errors. If you're doing well on one section of the test, but not well on another, you've got to rework your strategy on how you're actually taking tests. I mean, like I said, you guys are business majors. Numbers are your life. Think about it. Let's just assume, erroneously, if I had a lot of money, okay? And I want you guys to invest my money. Do I want a person working for a company handling my money that doesn't know how to run numbers? Lord, no. Why would I hire you? Why would you be working for a company if you don't know how to understand this stuff and work these numbers? Because you know, at the end of the day, I'm gonna teach you all this stuff, and then I'm gonna show you this interesting application to the business world of why this stuff is so important. This is why this class is such a prerequisite for so many other things. This stuff is incredibly important. You gotta be taking notes on this and studying this stuff every day, making sure you're mastering this stuff. It is that important. You've got to know this stuff, okay? And this idea of these concavities is going to be incredibly important as well. Understanding this concept of the rates of change of the rates of change. That is important, okay? So here's an example here. All right. So here's one from our Hawks TV example, but again, a different one. So I do want you guys, you've got a resource with the Hawk stuff, watch those examples that they put on the videos. And there's one just like this one, except we just changed the number. So given f of x equals 1/3 x cubed minus 2x squared plus x minus 3, determine the intervals on where f of x is concave upward and concave downward, and locate all inflection points. They're talking about concavity. The words, I mean, here's the thing. I'm going to take the exact same questions I gave you on the last test and change the words increase and decrease to the words concavity and make you do the same stuff over again, except concavity deals with the second derivative. So, to determine the intervals of concavity here, the first thing I'm going to do is calculate my second derivative. But to take the second derivative, don't screw it up. You got to get the first derivative right first. So what's the derivative of 1/3 x cubed minus 2x squared plus x minus 3? Well, 1/3 is a constant. Derivative of x cubed is 3x squared, but 3 times a third is just 1x squared. Minus derivative of 2x squared is 4x, and the derivative of x is plus 1. Derivative minus 3 is 0. But don't care. That's the first derivative. Don't need him. What I need is the second derivative. So I need the first derivative so I can get to the second derivative. Derivative of the derivative. So here we go. What's the derivative of x squared? 2x. Derivative of minus 4x is minus 4, and the derivative plus 1 is 0. Now, to get this hypercritical value thing here, aka the inflection number, what I'm going to do here is now I'm going to take my second derivative, which is 2x minus 4. I'm going to set it equal to 0 and solve. I'm going to add 4 to both sides. That gives me 2x equals 4. Then I'm going to divide it by 2. I'm going to get x equals 2. That is my hypercritical value. That is my inflection number. Okay? Now, to figure out, see that word right there? Determine the intervals. Anytime in a math problem you hear the word intervals, draw a number line. So I'm going to draw a number line, and this is going to be a second derivative number line, and I'm going to put my hypercritical value, my inflection number on there, which is 2. I only had one of them. It subdivides my number lines, and now I'm going to do test values. Pick a point, use your brain, less than 2. Good choice, 0. And I'm going to plug it into the second derivative. So I'm going to plug 0 into my second derivative. My second derivative is 2x minus 4, so it'll be 2 times 0 minus 4. That's negative 4. I don't care what the number is, what's the sign of it? It's negative, so everybody in that interval is going to be negative. And what a negative second derivative means is it's going to be concave downward. Now I'm going to pick a number bigger than 2. I choose 3. So f double prime, plugging in 3. This would be 2 times 3 minus 4. 2 times 3 is 6, minus 4 is 2. Don't care what the number is. The fact it's positive, so everybody's going to be positive. This means it's going to be, because this is a second derivative number line, it's going to be, bless you, concave upwards. Okay? So to answer the question here is this. Where are the intervals of being concave up? It is concave up between 2 and infinity. Where is the intervals of being concave down or downwards there? It's concave down between negative infinity up to 2. And once again, we always use open parentheses around my hypercritical numbers or any kind of critical numbers. Does that make sense? Same thing as what we did before. Now, locate all points of inflection. Now, look at it. This is my inflection number, as I call it, the hypercritical value. But look at it. I was negative concavity, and then I was positive concavity. I changed concavity. So x equals 2 is an inflection number. But they wanted a point. So to give them a point, I gotta have 2 comma something. How do I get that something? What do I gotta do to get a point? Outstanding. You gotta plug it into the original equation to get the y coordinate. Not the first derivative, not the second derivative, you get 0. Not the first derivative, you gotta go all the way back to the original function. So to get the y coordinate, y is gonna be equal to f of x is 2 here. And remember, this would be 1/3 times 2 cubed minus 2 times 2 squared plus 2 minus 3, and it's time for a handy dandy calculator on that one. So here we go. It'll be 1/3 times 2 cubed minus 2 times 2 squared plus 2 minus 3. I end up getting, I guess with that interesting fraction, I'll make a fraction here. I got negative 19/3. Does that make sense? Just a y coordinate, whatever it happens to be when you chunk it in. But you gotta go to the original function to get that y coordinate. Does that make sense? But notice the setup here, because you begin to see why that stuff we did in chapter 3 was so important, because here I am doing the same thing again, but on a different derivative level. And it's telling me different information. Now it's telling me about concave up and concave down. So, first thing we gotta do in terms of our practicing here is, we need to practice taking our second derivatives here. So, here we go. It says, find the second derivative of each of the following. F of x is equal to 2x cubed plus 5x minus 1. So, find the second derivative, you've got to find the first derivative first. So derivative of 2x cubed is 6x squared plus derivative of 5x is 5, derivative minus 1 is 0. This means my second derivative is going to be, well, derivative of 6x squared is 12x, derivative plus 5 is 0, and there's my answer. Second derivative is 12x. Oh, but how fast is it going to be before we actually have to get a little bit harder functions? Take a look at the next guy. The next guy is this. F of x is equal to x squared plus 7 squared. But once again, to get the second derivative, you got to do the first derivative first. So here's my first derivative. Well, to take the first derivative, what rule do I have to use to take derivative of x squared plus 7 squared? Chain rule. Derivative of the outside, inside stays the same time derivative of the inside. Derivative of the outside, the 2 pops out front, the inside, x squared plus 7 stays the same, raised to the subtract 1 first. Times derivative of the inside, which is derivative of x squared is 2x, derivative of 7 is 0. The next thing you should do is clean him up. 2x times, 2 times 2x is actually 4x times x squared plus 7. I could leave them like this, or because it only has a power of 1, I can go ahead and distribute and clean them up even further. I mean, I could use the product rule on this guy, and I'll get the right answer. And remember, on Hawks, you can type it in exactly the way it looks, but if I'm taking higher order derivatives, I'm going to clean it up the best I can first. So it makes it easier to take on the derivatives. So derivative of 4x times x squared is going to be 4x cubed. Derivative of 4x times a 7 is what? Plus 28x. Now, I'm going to take the second derivative. So notice how much algebra I'm doing on that first derivative. I'm cleaning them up before I take my second derivative. Derivative of 4x cubed is 12x squared plus derivative of 28x is 28. There is my second derivative. Does that make sense? Take a look at the next guy. F of x is equal to 3x divided by x squared plus 1. Stop, pause, hesitate. First you take the second derivative, you got to take the first derivative first. What rule are you going to use to take the first derivative? Quotient rule. Just to remind you, because spring break was a long time. Derivative of the top times the bottom minus the top, times derivative of the bottom all of the bottom squared. Then I got to clean it up. See, in the old days, aka the last test, I didn't make you clean it up, but now you got to, so we can take the second derivative. So, quotient rule. So labeling is everything in calculus, so here's your first derivative. Quotient rule, derivative of the top, derivative of 3x is 3 times, derivative of the top times the bottom, x squared plus 1, minus the top, 3x times derivative of the bottom, derivative of x squared plus 1 is 2x, all over the bottom, x squared plus 1 squared. But now I'm going to clean them up. To clean them up, I'm going to distribute the 3. That gives me 3x squared plus 3. Minus, I'm going to multiply the 3x times the 2x and get a what? 6x squared all over x squared plus 1 squared. And keep cleaning them up. Combine like terms. 3x squared minus 6x squared is a negative 3x squared plus 3 over x squared plus 1 squared. Does that make sense? Don't lose you guys anywhere. Now, take a second derivative. What rule am I going to use to take a second derivative? What do you see? Negative 3x squared plus 3 divided by x squared plus 1 squared. Quotient rule. Yeah, I see some chain rule action too, but the big picture, because of that big divide, is the quotient rule. Derivative of the top times the bottom minus the top times derivative of the bottom, all over the bottom squared. Derivative of the top, derivative of 3x squared plus 3, negative 3x squared plus 3. Derivative of negative 3x squared is what? Negative 6x, and derivative plus 3 is 0. So it's derivative of the top times the bottom, x squared plus 1 squared, minus the top, copy it, negative 3x squared plus 3, times derivative of the bottom. To take the derivative of the bottom, what rule do I have to use? The bottom is x squared plus 1 quantity squared. Chain rule, derivative of the outside, the 2 pops out front, the inside x squared plus 1 stays the same. Raise to the first power times derivative of the inside, which is 2x, all over the bottom, x squared plus 1 squared, squared, the bottom squared. So you even got a squared squared there. And a squared squared is going to make it what? To the 4th power. Now, I'm going to show you guys a trick on this thing. Derivative of the top times the bottom minus the top times derivative of the bottom all over the bottom squared. I just cleaned up that bottom squared. Now look at these two terms. Now what you got, terms are separated by addition, subtraction. It's a big old minus because of the quotient rule. If you look at these two guys, you'll have something in common. And whatever you got in common, factor it out. This is the fast way of cleaning this thing up, which is what you're going to need to do. If you look at these two guys, I notice that I have what? I have a, let's see here, a 6. I got a 2 times a 2, which is a 4, and I got an x in common. I've got an x in common. I officially have a 2 in common. I can factor out that 2. And I also have an x squared plus 1 in common. So I can factor out a 2x times an x squared plus 1. I'm going to put a bracket to show you what's left over. What's left over is going to be a negative, factoring a 2x out of a 6x leaves me with that minus 3. This is x squared plus 1 squared, but I pulled out one of those x squared plus 1s. That means there's an x squared plus 1 left over. Minus, I factored out the 2x. Let's just say that one's gone. So I'm going to be left with this 2, that 2 right there, this negative 3x squared plus 3, but that x squared plus 1 has already been factored out, so I can close my bracket there. I pulled out what's in common. Now, I'm going to clean this mess up. I'm going to distribute, and distributing is going to give me negative 3x squared minus 3. I'm going to distribute this minus 2. That's going to give me a plus 6x squared. And minus 2 times a positive 3 is going to be a minus 6. And then I'm going to finally get my final answer in all its grandiose factored form. It'll be 2x times x squared plus 1 times, what's left inside here? I've got a minus 3x squared plus a 6x squared. That leaves me with a 3x squared. Minus 3 minus 6 is actually minus 9. With me? divided by x squared plus 1 to the 4th. Are you done cleaning this thing up? What's the deal? You got something else you can do. What else can you do? Numerator, denominator, you see something in common. I got both having x squared plus 1. X squared plus 1 on the top. I got x squared plus 1 to the 4th, so one of them's going to cancel, leaving 3 of them left over. So that completely cancels one of those. So my actual answer for the second derivative is 2x. Officially, I can pull out a 3 if you want to. This is up to you. We'll take it either way. X squared minus 9 divided by x squared plus 1 cubed. And there's my answer. Or, for those people that are just, it bothers them to see something in common and because you're in factor mode, I can pull out a 3 out of this guy. And 3 times a 2 would be a 6x. And if I pull out a 3, that leaves me with x squared minus, I'll pull a 3 out of a 9, leaves me with a 3 over that x squared plus 1 cubed. Again, we would take either one of these answers, you're going to get it absolutely 100% correct. Because eventually you're going to take this thing, set equals 0, and solve. So you notice that it doesn't take much to make one of these problems with the second derivative get a little more complicated. A classic quotient rule will do it for you. Okay? Look at question number 2 here. It says this. Find f double prime of x and evaluate f double prime of 0, f double prime of 1, f double prime of 4. Remember, even with these second derivative stuff, this is still functional notation. Okay? So, first thing I got to do is get my second derivative. Well, derivative of x cubed is 3x squared, plus derivative of x squared is 2x, and derivative of 3 is 0. There's my first derivative. So my second derivative is going to be, well, derivative of 3x squared is 6x, plus derivative of 2x is 2. This is my second derivative. Now, here we go. We've got to find f double prime of 0, f double prime of 1, and f double prime of 4. According to the functional notation, what am I going to do? I'm going to plug these numbers into my second derivative. So this would be 6 times 0 plus 2. Well, that's easy. That'll be equal to 2. F double prime of 1, that'll be 6 times 1 plus 2. Well, 6 times 1 is 6 plus 2 is 8. And f double prime of 4, this will be 6 times 4 plus 2. 6 times 4 is what? 24 plus 2 is 26. There we go. Does that make sense? Part B, same thing, except, oh, they made them nasty. I got f of x is equal to the square root of x minus 4. Well, I don't do square roots. What's the square root? That'll be x minus 4 to the half a power. I need the second derivative. So we've got to find the first derivative. First derivative would be chain rule. Go to the outside, the 1/2 pops out front. The inside, x minus 4 stays the same. Raised to the subtract 1, that'll give you negative 1/2. 1/2 minus 1 is negative 1/2. Derivative of the outside, inside stays the same. Time derivative of the inside, derivative of x is 1. Derivative minus 4 is 0, 1. So I'm going to clean this up, and this would just become 1/2 times x minus 4 to the negative 1/2. Now, 1/2 is a constant. It's out front, and remember, first rule of derivatives is a constant times a function, constants hold over. So here comes my second derivative. That constant 1/2 just holds over. Just hold that constant right there. What's derivative of x minus 4 to the negative 1/2? Well, you bring your negative 1/2 down front, you get x minus 4 raised to the subtract 1. That'll be negative 3/2. Times derivative of the inside, which will be derivative of x is 1, derivative minus 4 is 0. Cleaning this guy up, positive 1/2 times negative 1/2 is a negative 1/4 times x minus 4 to the negative 3/2. All right, so here we go. We're supposed to find f double prime of 0, f double prime of 1, and f double prime of 4. So let's see what we get here. Now, I'm going to plug in 0. 0 minus 4 is what? Negative 4. What's negative 4 to the 3/2 power? And I'm going to just type it in. I'm going to show you. Negative 1/4 times 0 minus 4, which is negative 4, raised to the negative 3/2 power. But before I hit enter on this thing, I want to talk about it. Negative exponent just puts them on the bottom, so it's going to be a fraction. But 0 minus 4 is negative 4, raised to the 3/2 power. That 3/2 power, even though it's in the denominator, the numerator is meaning it's going to cube it, but that divide by 2 over 2 means it's what? Square root. What's 0 minus 4? Negative 4. What's the square root of negative 4? It doesn't exist because you can't take the square root of a negative number, right? So when I hit this, what do I get? Non-real answer error. The reason why is because I'm taking the square root of a negative number. So this answer, D and E, what does D and E stand for? Does not exist. Look at the next one. If I plug in 1, negative 1/4 times 1 minus 4 to the negative 3/2. Well, 1 minus 4 is negative 3. To the negative 3/2, that's 1 over 1 minus 4 to the positive 3/2. But the fact is it's a 3/2 power, and that 2 on the bottom means it's square root. But 1 minus 4 is negative 3, so I got the same problem. I'll just show you. I'm going to put it in here, plug in that 1 into it, and what I get, same old error message because I'm taking the square root of a negative number. However, 4 is different. Well, not really. What's 4 minus 4? 0. What's 0 to the negative 3/2 power? Well, this time I'm actually going to clean this guy up. So my second derivative, when you clean him up, it's going to be negative 1 over 4 times x minus 4 to the positive 3/2 power. When you plug in 4, I get 4 minus 4, which is 0, to the 3/2 power. 0 cubed is 0, square root of 0 is still 0, times 4 is 0. What you're going to get here is negative 1 over 0, but guess what you don't get to divide by? It's not the negative on a radical that's giving you a problem. It's a 0 in the denominator giving you the problem. It still does not exist. So that's wonderful 3 answers that just don't exist for you. Does that make sense? Just working the algebra and the math and stuff. So, on this next one, I'm going to pass back the test in just a second, but on this next one, what is the question? It says this: determine the intervals on which the function is concave upward and concave downward, and find all inflection points. This is the exact same problem that we did in the first problem that I started with. That word interval means I want a number line. So this one, I'll do this one, but the rest of them I'll have to do next time. But I need the second derivative. Well, the first derivative is going to be 3x squared minus 6x. Your second derivative is going to be, derivative of 3x squared is 6x. Derivative of minus 6x is minus 6. The first thing I'm going to do is get that hypercritical number. I'm going to set it equal to 0 and solve, get my inflection number. So this is my second derivative, keep them in reserve. I'm going to add 6, so 6x equals 6. Divide by 6, I get x equals 1. Intervals, I'm going to draw a number line. This is a second derivative number line, okay? And I put my inflection number, my hypercritical number on my number line, and now I'm going to do test facts. Pick a number less than 1. Good choice, 0. Plug in my derivative, that'll be 6 times 0 minus 6, that's negative 6, which makes it negative. Negative second derivative means it's concave down. Pick a number bigger than 1, I choose 2. F double prime of 2 would be 6 times 2 minus 6. This is 12 minus 6, which equals positive 6. I don't care what the number is, the sign is positive, which means it's concave up. So it is concave down on the interval between negative infinity to 1, and it is concave up on the interval between 1 and infinity. And because you change concavity there, you actually have an inflection point is at 1, but I need the y-coordinate. How do I get the y-coordinate? What am I going to do? Plug it back into the original equation. 1 cubed is 1. 3 times 1 squared is, well, it's just minus 3. 1 minus 3 is negative 2. Plus 7 is 5. I plugged into the original equation. There's my inflection point. Does that make sense? We'll do these other two, next time, and then we'll move on into section 4.1B.